Pressure. A book resting on a table exerts a downward force on the table. That force is the weight of the book. If the book's mass is m, that force is given by W, or weight, equals mg. G is the acceleration of unsupported objects near Earth, 9.8 meters per second squared downwards. And notice, you capitalize Earth, but if you put the word the in front of Earth, then you use Earth with a lowercase e. An important idea, especially when working with fluids, is pressure. To understand pressure, let's first look at the way that a book exerts a force on the table in a slightly different way. Think about the weight of the book exerting pressure on the table, where pressure is defined as force per area. In this case, force is just the weight of the book, and area is the area over which the book is in contact with the table. Pressure is the ratio of force to area. The same force can result in very different pressures. If a book is placed flat, its weight is spread over a large area, resulting in a low pressure. So we have less pressure here. Placed on its edge, the area is reduced, and since the force is the same, the pressure is increased. Once again, pressure is force per unit area. Since the units of force are newtons and the units of area are square meters, that's meters squared, the units of pressure are newtons per square meter. Let's work a problem. We have a 24 Newton book with dimensions of 4 by 2 by 1, all of them in meters. How would it be placed on a table to achieve the highest pressure, and what would that pressure be? How would it be placed on a table to achieve the lowest pressure, and what would that pressure be? The highest pressure is achieved when the contact surface is the smallest. This will occur when the book is placed with its 2 meter by 1 meter side on the table. That's a contact area of 2 square meters, right? 2 times 1, 2. So our pressure equation, force per unit area, we have the 24 Newton pressure, the 2 square meter area, and we get a pressure of 12 newtons per meter squared. The lowest pressure is achieved when the contact surface is the largest. And what's that going to be? The 4 by 2 meter side. That's a contact area of 8 square meters. Once again, pressure is force over area, 24 over 8 square meters, and we have a pressure of 3 newtons per meter squared. Now let's move from books to fluids. Fluids exert a pressure perpendicular to any surface. If you put a little cube here in the water, it's being pressed in on all sides by the water pressure, or the fluid pressure. The pressure at a given depth, and see that? That's the depth for all 3 of these containers. It depends only on the density of the fluid and the depth, not the shape of the container. The pressure on an object at a depth of h below the surface of a fluid is due to the weight of a column of fluid between the object and the surface. So the pressure is dgh. And on the previous slide, at each one of those levels, there was the same level for each of those containers. The pressure was exactly the same. The shape didn't matter. So D stands for density, G is gravity, and that always equals 9.8 meters per second squared on the surface of the Earth, and H is the height of the column of fluid above the object, or the depth of a submerged object. The density of fresh water is 1,000 kilograms per meter cubed. What is the pressure in newtons per square meter at the bottom of a swimming pool whose depth is 3 meters? So here's a couple constants that we'll be using with this problem. We list our givens. Here's the density of water, of fresh water, which is in your swimming pool, value of G, and here's your depth, okay, 3 meters. We use the pressure equation, density times G times H, and we put in the values. There's our density of water. Here's the acceleration due to gravity, and here's the distance below the surface of the water, and we get a pressure of 29,000 newtons per square meter.